Hi, so this talk is about electroweak precision measurements at the FCC-ee. The FCC is a future CERN project for a circular collider of 100 kilometers, and the EE program would collide electrons and positrons at energies from the Z-pole at 90 GeV up to the die-top production at 365 GeV. So this program, as you can see, is essentially a supersizing the LEP program, both on luminosity and in energy. It would deliver about 10 to the 5 times the amount of Z decays collected at LEP1. And for LEP2, that operated at only at 200 GeV, it's less clear, but in terms of W pairs, for example, it would almost deliver 10 to the 4 times. So we are looking into potential statistical improvements on the LEP measurements that are of the order of 100 or even 300 times. So that's pretty impressive. Just a brief slide to remind you about LEP legacy results that are still quite relevant now. A comment that while LEP didn't discover anything in hadron colliders has made the most recent high energy physics discoveries, the electroweak precision data at LEP and even before LEP have been very important in showing the way and indicating the direction for the future discoveries. For example, here you can see the LEP1 data, how indirectly it was constraining the top quark mass and indicating its value even before it was discovered, and more loosely also the Higgs boson mass. Okay, on the left here is the current electroweak fit from GFitter. You can see that a lot of the most important parameters that enter the global electroweak fit are still from LEP measurements and from the Z-pole in particular. Definitely looking at these kind of plots, where it compares direct and indirect determinations of these fundamental parameters of the standard model, one would wish to make measurements more precise here and to figure out if things are consistent or if there's something else going on. So on the right side, as a spoiler, I put directly the precision that is currently estimated from the FCC-ee physics program for these observables. And so the first column has the present value and error, and the second column has the potentially improvement from statistics of FCC-ee. So you can see there these factor 100 or more that I was discussing there. And on the third column are the current estimates on the systematic limitations, and most of these measurements are thought that eventually will be limited by systematic uncertainties. There are two detector concepts that are currently examined for the FCC-ee physics program. One is the click-like detector, and the other is the IDEA concept. They are pretty different and complementary in terms of their main tracking devices and calorimetry. So they provide these complementary ways to check potential precisions and systematic uncertainties. So let me quickly give you an overview of the Z-pole line shape and decay rates measurements. The data taken at FCC-ee around the Z-pole will be equally shared at the peak point at 91.2 and at two off-shell energy points a few GeV off at 87.9 and 93.3. This will allow to measure the full line shape and the Z mass, and with the precision that in this case will be limited by the knowledge of the beam energy. And there we know that resonant depolarization can be used and will be used on a continuous basis and for both beams here, and will lead to a precision of 100 kV. The off-shell data will provide an important direct measurement of alpha QED at the Z mass, which will be very important for the interpretation of the higher precision FCC-ee measurements for the perturbative calculations, as currently the bottleneck is the running of alpha QED and the hadronic contributions in the running. The forward backward muon asymmetry can be used as a self-normalizing quantity here and sensitive to the off-shell photon contributions. And the final precision on alpha QED will be a few 10 to the minus 5. And this has been optimized. And in fact, the two off-shell energy points for data taking are optimized exactly for this measurement. There's a number of decay rates that will be measured with very high precision. We all expect them to be limited by some systematic uncertainty here for quark decay rates and for lepton decay rates. The ratio of lepton decay rates to the hadronic decay rates is very clean and can be used to extract alpha S at the Z mass pole with precision here of around 10 to the minus 5. Among the other rates, it will be very important to verify RB, the rate into B quarks, to sort out the results from LEP. And here it will be important to understand the systematics from hemisphere correlations and how the detectors can be improved for that. The other very fundamental Electroweak measurements to do with the Z-pole are the asymmetries. We can measure the forward-backward asymmetries as done in LEP1 for all lepton types and for heavy flavor quarks. And taus can also provide the polarized measurement. So here on this slide are the various uncertainties that are estimated currently with the current estimates of systematic uncertainties. There are lots of improvements that can be done, can be thought of in these measurements. For example, in the heavy flavor asymmetries, the analysis can profit from more modern multivariate techniques that can combine informations from all particles reconstructed in the event, and rather than using simple jet charges as done as LAP. Ultimately, the golden channel for asymmetries is the dimuon again, and from here the weak mixing angle sine theta effective can be derived here with a precision that is expected to be below 10 to the minus 4. Moving to higher energy, the W pair threshold line shape can be used to measure both the mass and the width. So you need to take data at least two different energy points to measure both. One of them is a bit off-shell, and the other one is a bit above the pair production threshold. The precision, expected precision is half an MeV on the W mass with this method, and just a bit above 1 MeV for the width. And we expect here, this is a very clean measurement where we expect to keep systematic uncertainties under control, actually also learning from what done at the Z-pole. And these are the systematic control that will be needed for this kind of precision. And if you cross-check with what will be done with the Z-pole, these are much less stringent, so it looks feasible. Just an interlude here to say that a similar method can be applied to measure the ZH production threshold cross-section and to derive a very precise measurement of the Higgs mass. Here 5 MeV, so the order of the Higgs width. This is again a very clean measurement, would be a very clean measurement of the Higgs mass, and would allow us to plan then the measurement of the electron Yukawa coupling direct measurement running E plus E minus collisions at the Higgs mass of 125 GeV. The other way to measure the W mass and width is by kinematic reconstruction. Here, one can use all the W pairs collected by the FCC-ee program at the threshold and at higher energies, a total of 150 million W pairs. There have been some detailed studies done here with the CLD detector concept, and the ultimate statistical precision is very similar to the threshold method. So it's about half an MeV for the mass and 1 MeV for the width. But the systematic uncertainties are difficult to predict precisely. One of them is to control the beam energy for the kinematic fit, especially at the higher energy, with the higher energy data. One can imagine using other events like radiative returns and ZZ events to constrain that, or say to effectively measure the ratio of the W to the Z mass. Okay, the W data can provide also very precise measurements of the decay branching ratios, of leptonic and hadronic branching ratios. This will provide a lepton universality test that is currently at the few percent level, but would go down to the 10 to the minus 4 level. And similarly, a quark lepton universality test also at the 10 to the minus 4 level with the FCC data. The hadronic branching ratio can also be used to extract alpha S, this time at the MWQ square, with a precision of 10 to the minus 3, and from this formula here, set stringent test of the CKM unitarity for the first 2 rows of the CKM matrix. More directly, one can imagine to use flavor tagging on the decaying jets of W's to measure couplings to, for example, to C and B quarks directly, and therefore measured the CKM elements in this way. This has been looked into, and there's a potential, for example, to measure VCB at the per mil level with this data, which is currently known at the several percent level, and prospects to improve on VCB are very difficult. W pairs are, of course, can be used to set constraints on gauge couplings and look for anomalous contributions or FT contributions. Here, a study has been done at the 3 data taking energies of FCC, 161, 240, 365. The higher the energy, the more sensitivity. So these fit have been done using only semileptonic W pairs, decaying to electrons or muons, or a very simplified version. Still, the precision with respect to the LEP2 limits that are comparable to the current LHC ones is a factor 50 or so. So there's a lot of potential here, of course. And here, the high energy data is going to play a more important role. There is a lot of untapped potential in gauge coupling limits and EFT limits from other processes, other Ford-Fermi processes, Z pairs, and single W and single Z productions, where you can see here on this table, we also expect huge improvements with relative to the LEP2 measurements. And also, not studied yet, so our production also still at high energy of 3 massive gauge bosons and VBS processes. All of these, together with photon processes as well, can deliver very stringent EFT limits. Okay, so this is clearly a very rich and very amazing program of Electroweak precisions from the FCC-ee data, both at the Z-pole and above the Z-pole. There's a potential for improving the current precision by factors up to a few hundred times when systematic uncertainties are not that very dominant. And the large number of additional opportunities are shown given the huge luminosity and the higher collision energies. This MW top plot shows where we are now in terms of an Electroweak fit, where the LHC high luminosity could bring us, so not much further in Electroweak precision there, and where the FCC-ee data would bring us, both at the Z-pole and above. So there's still a lot of work ongoing and to be done to understand better all the measurement possibilities, to design these measurements, and to understand more precisely what eventual limiting systematics could be. Think again about how systematics can be solved or reduced, and go back to the detector design requirements in that sense. Thank you very much.